Hello everyone, my name is Emiliano Larach, and today I'm going to be going over lab number 4 for physics, where we will, physics 1 at Georgia Tech, where we will be looking at oscillations of a spring. A little agenda for this experiment will be first I'm going to do a brief introduction of important concepts, then I'm going to be looking at the observational data, which we got using Tracker, and then as a third step, we will be building the computational model prediction. We'll be looking at our code, how we set up to predict this motion we got from Tracker, and at the end, we will look at the results we got from our model and a little section called What If, where we'll be look over what happens if we change some variables in our experiment. Some basics are to calculate the movement of our object, we need to know which forces are acting upon it. The two forces acting upon our system in this case are the force of gravity, which always points downwards, and the spring force, which can point either upwards or downwards, depending if the spring is compressed or extended. Another important concept we will need is the energy conservation principle, which just states that delta E equals W. In this case, we're considering our work to be zero because our whole system, we're considering the Earth plus our spring as our system. So everything is just delta E and we don't have any work acting upon it. Since everything is our system, we need to know which energies are changing to be able to calculate accurately the changing energies. The energies that are changing in this case are kinetic energy, gravitational potential energy, and spring potential energy. Some important concepts and formula that we will need are the Newton's second law in both its velocity update formula and position update formula, the spring force, the spring force formula, the kinetic energy formula, the spring potential energy formula, and the gravitational potential energy formula, which will help us calculate the different changes in energy of our system and the total energy at the beginning, where we will look that something very interesting happens. For our motion in Tracker, we can see just by inserting the points of mass, the center of masses, we can see that the object starts following a elliptical orbit, elliptical trajectory, and we can see that it gets flattened as the object's velocity goes down. Then for our code, we first needed to set up the initial conditions. The initial conditions for this program are ball.m, which is the mass of the ball, which is 0.402 kilograms, which was given to us. Then we also have the position vector, which we got from Tracker, using our Tracker data, data given by Tracker, and also some constants. Important constant that we will have is the constant of gravity, the spring force constant, which we calculated using the oscillation periods in the y direction. We got 6.83, and the relaxed length of the spring, which was 0.123 meters. For calculating K, which is the kinetic energy, we simply use the kinetic energy formula we showed in the beginning. The spring potential energy, we also just applied the spring potential energy formula, and the gravitational potential energy, we just applied also the formula, and at the end, we just added them up to know the total energies. For the while loop, this will help us know the different energies and different positions when we load the data from Tracker. So we simply, for the gravitational force, we just simply ball.m/g, which is mg, and also for the spring force, we calculated in the loop, and we get the net force in each iteration of this loop. At the end, we also calculate the changes in energy at each step of our motion of all the data we got from Tracker. Then our model results were very interesting. As we can see here, the red position is the actual position and the blue position is the predicted position. This is the first is the y position and then is the x position. We can see they quite match up, but they're not exact, and we will discuss this later on. As we can see in our energy graphs, the energy principle does get conserved because our total energy, which is the blue, which is the orange line, it's just a constant line. Then the potential energy, we can see that when the spring is contracted, the potential energy goes up and the kinetic energy goes down. As we can see, the blue is the predicted motion and the red is the actual motion. So what does it mean? Is the energy principle satisfied? Yes. As we can see, our total energy doesn't change and it's always zero. Our change in energy doesn't change and it's always zero. So oscillation periods, we calculated the different times for each oscillation, And in the x-axis, it takes 1.24 seconds, and in the y-axis, it takes 1.53 seconds. This has a big impact on our calculations, and that is why we can see these variations between model and real predicted motion, because the different oscillations we have an impact on our k. So we would have a different k for spring motions or on x direction and on y direction, and this would involve more difficult physics concepts that we are not looking. So thank you very much for watching this lab. I hope you enjoyed it, and see you next one. Bye.